Hey guys, welcome to part three. So we were talking about K, which is the carrying capacity. Sometimes under lab conditions, that is where you are providing it all the nutrients required. So they're not really, there's not a foraging. They don't, the organism does not have to go out and find food, doesn't have to, and sometimes you might also be providing it an ideal environment where there is no unnatural predators, no toxins, nothing in that environment. It's a clean environment that you are providing in a lab setting. It might actually shoot above the carrying capacity, but then over a period of time it stabilizes and then comes back. So you can see this where these black dots indicate that it is shot over its carrying capacity, and then it kind of stabilizes around that carrying capacity and stays back here. The reason at this stage the death rate is equal to the birth rate. Remember, this is an controlled environment, so there's no immigration and emigration happening. Immigration and emigration. None of those things are happening here. So, excuse me. So this phase right here, the stationary phase that you're seeing, is basically death rate equals birth rate. Now human beings, we have talked about this in the apes class, that the carrying capacity of human beings might be 10 billion. We might very well shoot up over the 10 billion and still be able to live in that, because we have created artificial situations to allow for human beings to survive much longer. We have medical treatment that allows human beings to survive, well into their 80s. If you were to take the same human population and put them in the early man, hunter-gatherer society, an 80-year-old person who's not able to get their own food, who needs a lot of medical treatment, is really not going to survive. So, we kind of subsidize certain demographics, allowing them to survive. And similarly, like if you take all the number of kids that are like allergic to peanuts, those peanut allergy kids and kids with various types of food allergies would probably not survive, because there's no means of selecting for food out there. You just, if you were a hunter-gatherer society, you'd have to eat what is available. Nobody is going out there and testing and figuring out what foods you're allergic to, what foods you're not allergic to. So we kind of subsidize that, and so you could consider the living conditions with medical treatments, with technology improvement, and how certain things are subsidized by other people. I don't want to sound like really mean on YouTube, that's all. So because of that, we will shoot up over our carrying capacity. The other thing is, now when you get to the carrying capacity, it does not mean that it's always going to be stable. Within the carrying capacity itself, there could be a lot of fluctuations back and forth. That means let's assume that the carrying capacity was like at the 40 mark here. So things could go slightly above that 40, below that 40, above, below, so that's because, let's say there was a really bad winter and a lot of animals might die out, but not reaching the point where their reproductive pairs are dwindling. There's enough reproductive pairs to bring the population back up. And sometimes you could have a lot where you might have a really particularly good summer, where there's all summer and rains, so you might have a lot more food available, so there would be a lot more offsprings that would survive. But then, as population density increases, again, you have a lot more disease that happens because overcrowding happens, so the population comes down again, and then you're at, you kind of reach that, you're in and around that baseline. Population models are useful for understanding possible growth rates. So the density of a population is very, very important when we talk about how a species is going to survive in the long run. Because think about disease. How does disease spread? Certain communicable diseases that are that is infectious and contagious diseases tend to spread when people are living in close quarters. Because if you have people living, for example, if you get a cold and you come to school where there's a bunch of people in that area, more people will get sick. So if you get a cold and you're sick and contagious, don't come to my class. I don't want to get sick. But instead, if you are at home where you're not in minimum contact with different people, the less number of people will fall sick. So the population density greatly impacts that portion of it. Diseases spread faster in urban areas where the population is much dense than in rural areas or suburbs where the population is more spread out. So natural selection, population density plays an important role in natural selection. There are two types of things, and this is a very important concept. I need you guys to remember this. You definitely will have questions on this. Case selection is density dependent. The sympatric, where there's a big bang and there's a burst of number of seeds or a burst of number of eggs and sperm at one shot and then the animal dies, that reproduction is very density dependent. So let's say in the first generation there were more salmon than one could imagine, and so they're going to lay a lot more eggs. That means a great number of those, the density within that small upstream where they lay eggs is going to be much greater, which means a lot of those eggs are going to die. Sympatric is case selection or density dependent selection. Our selection is density independent selection. Human beings population, again, because of various ways in which we have subsidized disease, is density independent. How many kids we can have that heteropatric, however you want to call it, the second one, where lifelong you're able to produce offsprings, that is density independent. The survivability of the offspring is completely different. In this case, we're just talking about reproduction. We are not talking about how it survives. So survivability is definitely impacted by density within small broods or large broods, like we were talking about, when you have a large number of kids, each one of them gets less resources. If you have less number of kids, then more resources are distributed. But that does not impact how much eggs are, how many offsprings can be produced. Both R and K is kind of, people think of it as being very simplistic. Because there are many other factors that also impact how many adults are laying eggs, and how many of those eggs are surviving, how many of those eggs survive to adulthood and stuff like that. For example, if you take salmon, if there's a lot of salmon swimming upstream, if the density of salmon within that small upstream is very high, the bears will have a field day and eat a whole bunch of them, which will impact how many eggs they can lay. So we've talked about interactions between biotic and abiotic within the context of apes, and they both have certain impact on population growth. Climate has a huge impact on how populations of animals grow. If you have a particularly bad winter for a really long time, usually a lot of animals will die out due to starvation. If you have a particularly good rainy season and a particularly good summer with a lot of rain and stuff like that, good moisture and temperature, then a lot of animals will reproduce, live. However, once the density of those animals increases, then you have a chance of getting a lot more pathogens within that population, and then they'll die out. So one thing to remember is they'll die out. So density independent populations are usually the birth rate and the death rate does not change with population. Again, human populations is a very good example for this. Our birth rate and death rate does not change because of the number of people living in an area. It depends, it changes because of how much accessibility we have to resources. There's a high death rate in infant mortality rate in countries like in the continent of Africa, for that matter. That's not because there's a high density of people living there. It's because they have less access to resources. However, in a density-dependent population, if the density is very high, if there's already a lot of animals in that brood, the birth rates will fall and the death rates will increase. Why is that? Because if you have a lot of disease spreading within that population, if you have a lot of predation within that population, if there's a lack of space within that population, because to give birth to a baby and raise a baby, regardless of what the species is, if they are mammals. I'm taking mammals into consideration where there's considerable parental involvement. A birth rate will drop and the death rate will increase. Even in terms of plants, if you have a lot of plants living in a small area, the birth rates, the number of seeds that are going to germinate is going to fall because the resources are limited. For example, there's not enough space, there's not enough water to go around, so that's going to reduce the birth rate, increase the death rate. Once the death rate increases and birth rate falls, population density goes down, and again you'll have new seeds come in and populate that area. This is a graph that kind of gives you idea of how this works. This is pretty much graphical depiction of what I just blabbered on for like 10 minutes. We all know what a negative feedback loop is. So, like I said, when resources are limited, there is a negative feedback loop that happens that regulates the population control. You must remember what negative feedback loop is, what negative and positive feedbacks are. We talked about that in our molecular biology section. If you don't remember, come see me and I will yell at you. Within a crowded population, there is going to be higher intraspecific competition. So you know how I constantly get confused with interspecific and intraspecific? So I figured this thing out. Interspecific is between species because it's like interstate highways between states, which are always different species. For example, Connecticut is a different species from California. And intraspecific is like surface streets and they're in the state. That's how I figured it out. So there's going to be a lot of intraspecific competition for resources within that species. We talked about this in the context of apes. If there's an increase in population density, there's going to be more competition for all sorts of resources. There's also going to be a lot of competition for a mate. So mate selection becomes a big issue. Now, every time a population increases, this does not mean that population is going to increase at a 50-50, that males are going to be the same number as females. That's usually not going to happen. And we talked about this in terms of even how carrying capacity is affected by killing off of a male versus killing off of a female. If you kill off of a male, the male's job is to propagate as much as possible because the sperm is a cheap product. Cheap in the sense not that you can buy it for less, it just means that a lot of it is produced. The egg, on the other hand, is a huge investment. There's very limited number of them. So killing off a female might be a little better than killing off a male because the number of offsprings a female is going to have within a lifespan is actually limited by the number of eggs that she has, and not only that, by the number of times she comes in heat and how many babies she can have per litter. So all these are limited, whereas if you kill off a male is actually capable of siring more than one brood of offsprings with more than one female. So technically killing off a male is slightly more detrimental to the population size than killing off a female. Again, when we talk about male and female here, we are talking more specifically of reproductive age animals. If a baby deer dies, it is not a big loss to the entire population because we don't know for a fact if that baby is going to even be able to reproduce. So, and if something that's over the age of reproduction passes away, again, not a big deal. As cold as it sounds from a human perspective, this is a biology perspective. Again, I'm running out of time, so again, I think I can do this. Territory is a limits density. Space is the biggest factor that limits the population size.